Well, friends, in my last lecture, I talked about different isotopes of uranium, and you saw how all talk of nuclear energy production refers to some isotope of uranium. The naturally the fissionable isotope of uranium is U-235. It is only 0.7%, but uranium-238, which is the bulk of the matter, more than 99%, is a fertile material. It can be converted to plutonium-239, which is fissionable. And we saw that thorium can be converted to an isotope of uranium-233, which is fissionable. And this actually provides us the base root production of nuclear energy, because the eta value is the largest. Now, the question is then comes down to this. To start with, we need to separate uranium-235 first from uranium-238, and we will ignore uranium-234, which is such a small fraction of naturally occurring uranium isotopes that we will ignore that. So, essentially we come down to separation of uranium-235 and uranium-238. How do we do that? How do we separate, take out uranium-235 to start with? Now, essentially we have to first produce a compound, pure compound of uranium. And you know that the chemical properties of isotopes are always similar, no matter what element you have. If you have different isotopes, they will undergo the same reactions, they are the same. Like in hydrogen also, we have different isotopes, but when water is reacting, all the isotopes react in the same manner. So, when uranium is reacting as an element, the different isotopes all react in the same manner. So, you have to first produce a pure compound of uranium. It can be, you have to recover uranium from solution, either the acid solution or the alkali solution. We can precipitate an uranium compound, and we can also go through ion exchange and solvent extraction methods to get a pure compound. It is only when you have a pure compound, then we start talking about separating the isotopes uranium-235 and uranium-238. One technique is centrifuging. You must have heard about this word centrifuging. That suppose we have the two isotopes, two compounds in solution. Now, if such a solution is rotated in a very high speed, so like in any centrifuging, the heavier ones and the lighter ones get separated. So, centrifuging can be one way of separating. So, this is often a critical technique in the development of nuclear energy. How do you separate by centrifuging uranium-235 and uranium-238? There is another method of separation which is in this picture, that is by gas diffusion. Now, centrifuging made use of the fact that one isotope is heavier than the other isotope. Gas diffusion also make use of the same fact, that one isotope is heavier than the other isotope. Let me first tell you how it is done, then we will come to the principle. Essentially, this gas diffusion will be in the gas phase. The uranium compound in a gas phase is supplied from one side in a chamber where there are two compartments separated by a porous diaphragm. Now, when you talk about a porous diaphragm, we are talking about porosities of the atomic sizes. It is a very fine diaphragm. What happens in this, that in the gas phase, all the isotopes forming the particular compound or compounds with different isotopes, they are all moving around in different directions with different speeds. But eventually, after a while, what will happen is the lighter atoms will more selectively go through the pores in the diaphragm, and the gas that goes to the other side will be richer in lighter isotopes. So, we get an enriched material in terms of uranium 238. So, uranium 235, uranium 238 and uranium 235 isotopes in the gas supply gets differentiated, because the lighter ones will penetrate these pores preferentially, and so we get an enriched material which would have a higher proportion of uranium 235 than compared to what there was previously. Of course, this has to be repeated many times. This is a very simplified way of presenting it. Why should this happen? I have written it here very briefly. You know, in a gas, the average velocity of gas molecules can be calculated in many ways. If you assume a Gaussian distribution, you can think of the more probable velocity, you can think of an arithmetic average, but more meaningful is the root mean square velocity. So, we say that average velocity of gas molecules moving at random is inversely proportional to the square root of their masses. Square root of their masses. In a closed chamber, lighter molecules bombard a given wall with a greater frequency. If there is a membrane, then more lighter molecules go to the other side. So, all the gas molecules that are bombarding this membrane at random all the time, moving amongst themselves, colliding with each other, there is a velocity distribution amongst all these input gas molecules also. There is a distribution of velocities, because they are constantly colliding with each other, but there is an average value. That average value for the lighter isotopes is higher. So, because there is average velocity is higher, they would be bombarding this membrane more frequently, and therefore, more of the lighter isotopes will go through to the other side. That is how from a normal proportion we get an enriched material. So, more U235 will be here in one stage. Now, how it is exactly done in multiple stages and what are the other intricacies of this thing, we need not study. But basically, it is done by centrifuging or by gas diffusion. Different countries adopt for different methods, and perhaps some countries employ both the methods. I do not know exactly how it is done in India, which is applied where. But basically, the reason why I am mentioning it to you is that the nuclear metallurgy is based on the central theme, that you have to have uranium, and to start with you must have a method of separating the isotopes of uranium. One isotope which is lighter is fissionable. It will give fission reaction when bombarded with thermal neutrons. Those thermal neutrons can be used to bombard the isotope which is higher in value U-238, it will get converted to plutonium-239, which is fissionable. And then apart from this, if you have thermal neutrons bombarding thorium-232, we can produce another isotope of uranium, which is uranium-233, which can also undergo fission reaction and do that far more effectively than either uranium-235 or plutonium-239. So, it is basically the interplay of all these things. Now, I mentioned to you that we are actually, when you are talking about uranium, we are not talking about an ore like bauxite or hematite, where things are high grade. We are talking about ores where the metallic value percentage is very low. For example, I am talking about here the chemical beneficiation of Jaduguda uranium ore. We have in Jaduguda in Bihar uranium deposits, ore deposits which contain uranium. There are one or two other places, but they are not yet so important. Now, here the ore analysis is like this. Uranium is only in the form of U3O8 is only this actually 0.0, it is not sorry correct it, it should be 0.06 to 0.07 is as small as that. Please correct it or check the book I have mentioned, there is something wrong here. Silica, most of it is silica, then there is iron oxide, there is alumina, there is TiO2, there is MnO, there is calcium, there is magnesium, there is some P2O5, but essentially it is a siliceous material containing small percentages of U3O8. So, it is take it as you remove it 0.07, 0.08%. What do you do with such an ore? It is such a low grade ore, but there are processes of getting a concentrate and pure U3O8. Let us see how it is done. Again, do not be scared by the flow sheet, it only talks about the logical steps. As always, when we start with this ore, the ore particles would be 7 to 10 centimeter size in a big particles, which are basically siliceous material containing small amounts of uranium. It will be crushed into 10 to the power 10 to 15 centimeter size. Then crushing is to that kind of size. Then you go for grinding. You can never take a big particle and grind it. Both the things are comminution, but when we come to from big particles to sizes like this, we call it crushing, and we crush particles further, then we call it grinding. Grinding means we are going to minus 200 or minus 300 mesh. If also in the case of sulfides, we have to go to that kind of thing for flotation. Why do we grind to that size? Because when you grind, your leaching reactions will be more effective. There is a far greater surface area. Powders will react much more effectively with acid or alkali. Like in a sugar, when it is much finer, it dissolves faster. So, now here in Jaduguda, we are going for a H2SO4 leaching. Of course, after grinding with thickening, filtration, etc., these are simple process of getting a because when we do the grinding, we do wet grinding. We are putting water, because when there is a even at home, when you do some masala grinding, you put some water, because in presence of water, grinding is often more effective. Why it is so, I would not discuss it now, but there are fundamental reasons for that. So, when you have lot of excess water, that will have to go. So, we remove that water by thickening filtration step. Then we go for leaching. Sulfuric acid, why do we put pyrolusite MnO2? MnO2 is an oxidizing agent. So, it makes the action of acid even more strong. Then we will have filtration, a cake which is the insoluble material will go, uranyl sulphate will be in solution. See, from an ore which had so little bit of uranium, now we have got uranium where you have 0.7 gram per liter of uranium, which is fairly large. At least you have got the muck out of the system. Now, it has to go through this ion exchange elution techniques. It is a solid through which it will go, it will get absorbed, then it will be eluded out. So, we have discussed that. So, and in ion exchange, the ion exchange resin is constantly regenerated, and we get after elution a solution where uranyl sulphate goes up to 5 grams per liter. Then we go through some chemistry steps. If we add lime, iron will be precipitated, it will be separated out as a cake, purified uranyl sulphate solution. Then by adding MgO, we will produce after filtration uranium concentrate, which will be 70% U3O8. So, you see how beautiful these steps are. You are starting with a raw material which has 0.07% uranium and all the other things that you do not want. And from there, by these steps, you have come up with a concentrate with 70% U3O8, 70%. Now, what operates, I wrote this quite some time ago, the plant capacity was 1000 tons per day, chemical used were sulfuric acid, pyrolusite, sodium chloride, just to give you the scale of operation. Now, from that oxide, we have to go through some more purification steps to produce a pure oxide and finally produce UO2 or chlorinate to UCl2 or fluorinate to UF2. I am not going to go into those, that is exactly how you do that. I think it is not necessary, but you get the idea. You start with a low grade ore, you produce an oxide 70% U3O8. There are some other things, you have to purify it further, then you have to convert it to by some simple chemical steps to pure UO2. You can chlorinate it by using carbon and chlorine or carbon and fluorine to either chloride or fluoride. Now, in theory then, once you have the chloride or fluoride, you can go for metallothermic reduction. You can go for metallothermic reduction of the oxide also, like in the case of ferroalloys you will remember. In ferroalloys, when we produced by carbon reduction, there was a danger of carbon contamination. So, we produce high carbon ferrochrome and but we could avoid having carbon in ferroalloys if we went for metallothermic reduction. Here also, if you have a pure oxide, we can reduce by sodium or calcium, produce the metal, no problem. Also fluoride and chloride can be produced by metal, but then we have to see three things that I mentioned earlier. First of all, we have to look at the free energy of formation. We would like to only go for those reactions where free energies of formations are negative. Now, here it is positive, means to make it feasible, it can be made feasible, we have to drive the reaction to the right. If you take uranium into some kind of an alloy, or if you take out Na2 into some kind of a slag, this reaction may go to the right. Because remember, delta G naught standard free energy change does not change too much with temperature. But in some other cases, it is already highly negative. So, the reaction is thermodynamically very feasible. So, you find it is highly negative when there is a calcium reduction or magnesium reduction. In this case also negative values are there for calcium reduction, magnesium reduction, also there is hydrogen reduction. But trying to reduce an oxide by hydrogen is a very tricky thing, because there is a lot of precautions are necessary. Normally one avoids hydrogen in a pyrometallurgical process. Coming to reduction of fluorides, you find magnesium, calcium have negative free energy change, sodium also, potassium also. Again in the case of chloride, magnesium, calcium, sodium, potassium, they all have negative values. Now, what do we choose? We have so many choices to produce uranium: by metallothermic reduction of oxide, metallothermic reduction of fluoride, also chloride. Now, there the other criteria will come into picture. What is this physical state of the reducing agent? What is the physical state of the products where slag metal separation will be easy, etc., etc., etc. For example, often you can say that if you want to reduce by hydrogen, then you are talking about a closed reactor. After all, how will you keep hydrogen? And obviously, if you can increase pressure of hydrogen, things would become easier, but you need a bomb, you need a closed reactor. Here we are talking only about delta G naught values. We are not talking about what is the heat available from the reaction. If there is a lot of heat coming out as exothermic heat, that reaction would be preferable to some others. Some of these factors I am discussing in the write up at the bottom. Read this. The calcium reduction reaction is the most highly exothermic, not shown here, but calcium always exothermic reduction is highly exothermic. It produces sufficient heat to heat the charge, melt both slag and the metal for a good clean liquid separation. In practice, however, this is one. In theory, this is good. In practice, however, there is dissipation of heat, because no matter where you do it, you can't really keep all the exothermic heat with you. There will be a lot of dissipation, and because of dissipation, a pyrophoric metallic powder dispersed in the slag phase is produced. Say for example, you talk about the calcium reduction of uranium trichloride. You have produced calcium chloride, which is in the liquid slag, and uranium. Uranium is not going to be liquid, it is very high, the melting point is very high. It will not be in consolidated form, there will be powders dispersed in calcium chloride phase, which is not a very happy situation, but there is nothing you can do about it. And this metallic powder is, mind you, pyrophoric, so long it is dispersed in the slag, it is okay, but it can very easily react with the atmosphere. Now, sodium and potassium reductions are less exothermic. Also, the low boiling points of these metals like 880 and 760 necessitate the use of high pressures. So, like hydrogen, if you want to try to reduce by sodium and potassium, we will also need a closed reactor, because at the temperatures where we want to produce a liquid slag, they would become volatile. So, it will not occur, it will not be favorable. Especially if uranium is to produce in the liquid state, melting point of uranium is 1130 degrees. If you want to produce it in solid state, it is okay, but ideally you would like to produce a liquid uranium and liquid slag, which will cover the uranium, so that uranium will not get reoxidized. Now, if you want to produce liquid uranium, you need 1130 degrees. You cannot use sodium or potassium as reducing agent, because they become volatile one at 880 degrees, another 760 degrees. So, you need a closed chamber. So, all these parameters rule them out. You need convenience, you need something which is in practice can be carried out without too much of hassle. That is why we have to fall back on calcium or magnesium, and we have seen the calcium is very highly exothermic. So, we will go for calcium reduction. That is how we choose a metallothermic process from a choice of so many. So, the free energy of formation is not the only guide, it is one guide, but there is also heat of reaction, there is also physical state of reactants and products, all these are important. Okay. Now, we will talk about extraction of plutonium. I have mentioned and I will mention it again that plutonium does not exist in nature. It is produced by neutron bombardment of uranium 235, which is fissionable. But then when uranium 235 is undergoing fission, it does not mean all of uranium 235 at a time is going to produce neutrons are produced, and those neutrons, when you bombard uranium 238 to produce uranium 239, not all that uranium 239 is becoming uranium 230 is plutonium 239. That does not happen. When the thermal neutrons coming from the fission of uranium 235 are allowed to bombard uranium 238, only tiny fractions of that uranium 238 will get converted to plutonium 239. This plutonium 239 has to be separated from irradiated mass, irradiated 238. It does not mean the rest of it useless, it has to be irradiated again, that is a separate matter. Now, this is an enormous task. I do not know how many of you have studied the story of Madame Curie. When she first, Madame Curie and Pierre Curie, when they first produced radium, they had to process tons of pitch blende day in and day out through many steps in chemistry and chemical engine to finally produce that element which is called radium. Similarly, in case of plutonium also, there is small fractions of plutonium produced because of irradiation of uranium 238, and they have to be extracted. Now, chemical engineers have perfected the method. It is a very complicated process which I have discussed in my book. Do this, then do that, then do this. It is a matter of knowing where to find it. As I mentioned, you need not know, but you should know where to find it when you want to know. I have given you one reference, but there are many other books, especially those monographs published from BARC. You will find the production of plutonium 239. It itself is a very interesting material. There are several isotopes of plutonium 239. I think there are 6 of them maybe, and is highly toxic material. The tiniest amount of plutonium in the air or in the drinking water system can bring in deaths of hundreds or thousands of people. So, it has to be handled very carefully in glove boxes, in complete isolation. It is a science by itself, it is a technology by itself, but our scientists and engineers have learned to do this. So, I will not go into the intricacies of isolation of plutonium from irradiated mass of uranium 238. Please read it up. I will just come to emphasize as to how the same kind of principles will will be considered when we want to produce plutonium from a compound. Now, first of all, the aim of all these isolation techniques would be to use chemical engineering techniques to produce PuO2, then convert it to PuF4 or PuCl3, again for calciothermic reduction. Again, various considerations show that calcium reduction is the best way of going at it. In theory, there can be many. We can talk about a metallothermic reduction of the oxide or several metallothermic reactions for the halides, chlorides and fluorides, but calcium seems to be the best bet. Now, here one special technique is used, which is also of general application in many cases. During the reduction of PuF4 or PuCl3, we also use what is known as a booster reaction. Booster reaction boosts the availability of heat, and it does some other things. How does it boost? The booster reaction is that when we are adding calcium as a reducing agent, we also add some iodine. So, at the temperatures where reduction takes place, calcium reacts with iodine to produce calcium iodide, CaI2, is highly exothermic, it produces heat. So, it supplies heat for calciothermic reduction, so that the metal and the slag they melt. In addition, it does another trick. It produces calcium iodide, which dissolves calcium fluoride or calcium chloride, whatever is being produced, to form a low melting slag. See the trick, by making calcium and iodine react, we have first of all supplied heat, so that the plutonium that is produced and the salt slag that what I call is produced, they can melt easily. At the same time, we ensure that the salt we are producing, that calcium fluoride or calcium chloride, that F and Cl is coming from that plutonium compound, they form a low melting slag because they will dissolve in calcium iodide. So, calcium iodide plus CF2 or CaCl2 or being a mixture would have a lower melting point. So, a low melting slag will be formed. So, we have a low melting slag and a metal. This calcium reduction is done in a bomb reactor in an inert atmosphere, because plutonium is very highly reactive. If there is any oxygen, it will go back to that oxide form. Essentially, the reactions could be plutonium PuF4, calcium reduction plutonium CaF2, or plutonium trichloride can also be reduction, and it will be calcium chloride. And as I said, when there is a calcium iodide in the system, the chloride and fluoride will mix with calcium iodide to form a low melting slag. This is basically the trick. Now, let me just give a hint of the enormous complexity of how plutonium is recovered from this spent fuel, means from the you have U230. So, you have a spent uranium fuel treated by hydrogen HNO3 NaNO. It goes through filtration step. Solution would have both uranium as well as plutonium. Solvent extraction by tributyl phosphate, and then stripping will bring plutonium in the solution. Organic phase will have the uranium, which will be needed again, but we have taken out the plutonium. It will go through ion exchange, elution, etc., etc. Finally, an oxalate will be precipitated by adding oxalic acid. Calcination will produce PuO2. It is not very easy. It is very easy to show all this, but from the spent fuel, this is the way they will get the tiniest fractions of plutonium which have come as a result of the reaction of U-238 that has given rise to plutonium. Okay. Now, we will come to thorium. Now, thorium has other uses. It can go in for making ceramics. It could have some alloying applications, but we are looking at it from the point of view of nuclear metallurgy. There, as I said, thorium is not fissionable, but it can be converted thorium-232 to an isotope of uranium which does not exist in nature, uranium-233, which would be fissionable. And it is the most effective fissionable material because it consumes some neutron, but produces much more neutron than the other cycles. Now, the thorium ores are in plenty in our country, and we are very lucky that way, and that is why they are found in the beach sands of South India, both western coast and eastern coast. They have different composition of course, and their export is banned. It has been banned for a long time. In the beach sands, thorium exists as some simple oxides like thorium uranium O2 or thorium SiO4 called thorite, or there can be very complex oxides containing one or more of all these materials: yttria, Er, calcium, niobium, tantalum, iron, titanium, cerium, zirconium, lead, tin, and complex phosphates and silicates in a very complex manner. In common in beach sands of India, we have a thing called monazite. Monazite is usually written like this: lanthanum, cerium, yttrium, thorium, PO4. Indian monazite resources are the richest and most extensive in the world, and we are hoping that someday we will come to this thorium cycle and will produce from thorium the U-233, which will give us the nuclear energy in future. But to come to that, we have to first have uranium-235 and plutonium-239. Initial stages will need those. Now, here is a table which gives the composition of various monazite deposits in different countries. These are the countries: India, Brazil, USA, South Africa, Madagascar, and these are the main countries. You will find in our monazite the thorium TiO2 content is very high, U3O2 is low. There are lots of rare earths. Rare earths are very important elements. Actually, rare earths go for making flints. The lighters you have, they are made of rare earth materials, metals. There is C2O3, P2O5, Fe2O3, TiO2 and silica. Of course, this monazite is associated with TiO2 separately, to that I will come separately, but then in monazite there can also be small amounts of TiO2, that is the TiO2 being shown. So, anyway, the sum and substance is Indian monazite is supposed to be very rich in thorium content and rare earth content, and this monazite will come from processing of beach sands, which I have discussed in one or two lectures, that beach sands we process in Kerala, also in Orissa, for getting TiO2. We are looking at ilmenite. ilmenite is FeO-TiO2, we take out ilmenite, then produce artificial rutile, means remove FeO2 and produce TiO2. But then the rest are not to be wasted, that is where we have monazite, we have rare earths, we have many other things. So, but it will all coming from beach sands, and I mentioned some of these beach sands look black because of the very high TiO2 content. So, this TiO2 that is being shown in this table is only the TiO2 that is associated with monazite fraction. Now, the monazite comes from separation techniques employed on beach sands. Again, there are beach sands of Kerala, there are beach sands in Madras, Chennai, there are beach sands in Orissa coast. This beach sands, when sun dried, has composition in this range. They are mostly ilmenite, 60 to 75% ilmenite. That is what makes it black. Ilmenite is FeO-TiO2. And I remember mentioning also that in the place where olive ridley turtles come to lay eggs, and they come in thousands, and it is now a protected area. It is, we believe, we have worked on the how the olive ridley turtles come to the beach. The sand is absolutely black. It is so rich in ilmenite, and I think because it is so black, it absorbs sunlight and remains quite warm. Even during the month of February, the sand is warm, and I think it is very good for incubation of the eggs of these olive ridley turtles. I think that is one reason why the olive ridley turtles come to that Gahirmatha beach. Now, the government of India or nobody with their senses will try to take out that portion of the beach sands, because you will be interfering with the entire ecology of the system. But fortunately, we do not know how much of what is there, although there has been some work, but there are other beaches where also we have very rich in ilmenite and other things. So, but as I said, the blackness is because of the richness of the the ilmenite content, and that is why the olive ridley turtles go there. Anyway, coming back to the sun dried beach sands, which are available plenty along our coastline. Ilmenite is 60 to 75%, mostly ilmenite. Then there is garnet, 5 to 6% zircon, which is oxide of zirconium oxide, 2 to 4% rutile. Rutile is only TiO2, no FeO in it. 0.5 to 5% monazite, it varies from place to place. 8 to 28% silica and others. It is this monazite that we are talking about now. About this ilmenite fraction, I will talk later when I talk about titanium, and we have discussed it once. Now, after screening, it has to be first the sun dried beach sands are screened to remove lime shells, all kinds of things. There are shells all over the coastline. All the sea creatures come and leave the shells. So, the lime shells will go. There are also trashes, they have to be removed. Then it will go through low intensity magnetic separator. Ilmenite can be removed with low intensity magnetic separation, because it is highly magnetic. You do not need strong magnetic field. Ilmenite can be very nicely separated, is highly paramagnetic. Then from the tailings, high intensity magnetic separator removes monazite. Monazite is weakly magnetic. That is how we will get monazite out of the trashes. Now, there are other constituents which are removed by electrostatic separators or air tables. Air tables is another way of separating depending on their density, particle size, etc. Then after we have separated monazite, essentially by magnetic separation, it has to go for chemical treatment, which as I mentioned can be by acid leaching or it can be by alkali leaching. In our country, for reasons that I do not know, our people have opted for alkali leaching of monazite, and the flow sheet is like this. I will quickly go through. We have produced monazite from beach sands by separating it out by high intensity magnetic separator. Then it will go through grinding. We do not need crushing, because beach sands are already small particle size, but we need grinding to take it to -300 mesh. When you are going for alkali leaching, actually you need finer particles, because as I said, alkali is not as strong a reagent as acid in terms of leaching. So, we need very fine particles, and then the digestion would be at higher temperature 150 degrees, which means you need autoclaves. Why we need it? Because you are going for alkali leaching, and alkalis are weak leaching reagents. You need higher temperatures. You cannot go to temperature higher than 100 degrees. You need autoclaves where there is higher pressure and your boiling point of water will be raised. Recall the leaching of alumina in sodium hydroxide. There also we needed autoclaves, and sometimes we needed high enough pressure, so that the temperature exceeded 200. There are also alkali leaching which goes up to temperatures like this. In this case, the digestion is done at around 150 degrees with excess soda. Soda by monazite is equal to 3. If we filtrate, we get a residue and you get a solution. What will go in the solution? That is, so crystallization filtration, we will find that we have things that we are not interested in that. From this we actually recover NaOH that can recirculate it. But it is the insolubles which now has what we want. So, this is a very special kind of an alkali leaching, where the solution is not what interests us, but it is the residue that gives an hydroxide cake which will be leached by HCl, which after filtration will give us a thorium concentrate, and a filtrate will give us a fraction where we have rare earths, chlorides, carbonates and hydroxides. Now, here there is a very interesting point. So, now you see, you do not always leach to take out the values you are interested in solution. The idea of leaching is separation of the metallic values you are interested in and the things you are not interested in. Normally, by leaching we take the metallic values into solution. Like in the case of alumina, when you leach by sodium hydroxide, aluminum becomes sodium aluminate in solution. What does not dissolve contains iron, titanium, etc. Here it is opposite. What does not dissolve forms a cake which has the metallic values thorium and rare earths. It happens in alkali leaching process, may not happen in acid leaching. That is one advantage perhaps which has attracted people. So, once you have a hydroxide cake, that has to be leached by HCl, and after filtration there will be a residue which will be thorium concentrate, because this acid has not dissolved thorium, but it has dissolved the rare earth chlorides, carbonates, hydroxide. So, we separate here thorium and rare earths. The rest of the thing are not of much interest to us, excepting that in this process we can use regenerate sodium hydroxide, which will be recycled to the registrar. Now, let me read what is there at the bottom. The hydroxide is dissolved in HCl, then NaOH is added to adjust the pH to around 105. Now, we are going through a selective precipitation process. Now, we are going into pure chemistry, that once we have the thorium concentrate, which is in hydroxide or other hydroxides, we can take them into solution and precipitate one after another by simply controlling the pH of the solution. Typical chemistry, we have done such chemistry experiments. If I read it out, it will become clearer. The hydroxide cake is dissolved in HCl and then NaOH is added in order to adjust the pH to around 1.05, when most of the thorium is precipitated out. Subsequently, at a slightly higher pH, that is 2.3, rare earth phosphates are mainly precipitated. Uranium, if there, is completely precipitated at pH of 6. The basis for the selective precipitation of thorium, uranium and rare earth metals is indicated in figure, and essentially thorium ions reacting with this thorium phosphate. Now, by adding an alkali, the hydrogen ions are removed and the salt is precipitated. Now, I will just finish by saying it is a typical chemistry thing. You have in solution thorium, some uranium, rare earths. They can be precipitated out of solution simply by adjusting the pH. This is one example. There can be many such examples. Typical reactions I have mentioned here, the rare earth phosphates in H2SO4 will form this, thorium phosphate will form this. At no time is separation of uranium, thorium and rare earths can be complete when we are trying to precipitate them. Like thorium is precipitated at pH 1, means highly acidic solution. Rare earths at a slightly higher pH, uranium at even at higher pH. Supposing the pH was adjusted here, then percentage recovery of uranium would be this and percentage recovery of rare earths would be this, percentage thorium would be here, even above that, which means very rarely it is totally selective. Here a lot of rare earths will come, lot of uranium will also come. If you are somewhere here, neither rare earths nor uranium is being precipitated, but you can take out almost 100% thorium. So, almost 100% thorium can be taken out without any rare earths or uranium, but rare earths and uranium precipitation it's not that selective. No matter where you go, unless you go very pH value of something like this, you will have some rare earths. So, well, I will stop here for now just by saying, as we did in the case of uranium and plutonium, here also we have to, when you come to thorium, you have to produce a compound, and the compound can be an oxide or a fluoride or a chloride. Then we have to think about again a metallothermic reduction. Again we will think of the same criterion: free energy change, enthalpy change, physical state of reactants, physical state of the products, which will be convenient in practice. So, I will discuss that for thorium, and you will find things will be so similar to what we have discussed for uranium. Similar principles operate everywhere, and that is why it is necessary to try to find out where are the similarities, where are the dissimilarities. That is the basis of knowing the subtle differences in the extraction processes. Thank you. I will continue with that in the next lecture.